Okay, hi guys. Okay, so today I'm going to take you on a virtual tour at one of the attraction spot at the city centre of Malacca. Okay, jom, let's go. Okay, so as you can see, on my left side is the Malacca River, and straight ahead there's a little bridge called Jambatan Datuk Muhammad Zain, which allows vehicles to cross over the Malacca River to go to the shore residence. The bridge is made up of a particular structure which is joined together to support the weight of the moving vehicle. That structure, my dear friend, is what we call the truss, and that is what we are going to explore in this module. At the end of this course, you are expected to be able to perform computational analysis on 2D structure using the method of joint. Although the structure of the bridge looks like it needed a three-dimensional kind of analysis, but it can actually be simplified using a 2D analysis. So basically, the load coming from the vehicle crossing the bridge would be subjected to the deck of the bridge. These loads will then be transferred to the stringes, which will then be transferred to the planar truss. So observe the loading transition from the deck to the stringes to the joints of the truss. If we take out that truss element alone, then the load subjected to the bridge is equal to the load on the joints of the truss, as you can see here. Don't forget the reaction load at the roller joint and at the fixed joint at each end. You see? From this diagram, you can actually proceed to the computational analysis using the two-dimensional model only. Life gets so much easier at this point. Okay, now let's look at an example on how we can use the method of joints to solve computational analysis on a 2D structure. Okay, this structure consists of beams which is interconnected at three joints, which is joint A, joint B, and also joint C. The big question is, which joint is the starting point of our analysis? Before we proceed, let's just draw the reaction forces at each connecting joints. So there's a pin joint at joint A, and the reaction force would look like this, and there is a roller joint at C. Reaction force at joint A and C is unknown, and the only thing we know is that there is a known force of 500 Newton at joint B. So the important consideration when solving using the method of joint is to start at a point where there is at least one known force and only a maximum of two unknown forces. So as you can see from the structural diagram here, the only joint which fits this criteria would be joint B. So we are going to start from joint B. If we take joint B as the free body diagram, we know there's a 500 Newton horizontal force. Now, if we section out beam AB, the force acting on B would look like this. Accordingly, if we section out beam BC, the force acting on B would look like this. Resolving the FBC into X and Y direction would definitely make our calculation much easier. From here, we can use the equilibrium condition, whereby summation of forces in X direction would be equal to 0. So summation of these two forces would be equal to 0. As there is only one unknown in this equation, you can easily calculate the magnitude of FBC, which is equals to 707.1 Newton. Okay, so now you repeat the same step for the Y direction. Summation of these two forces would be equal to 0. Therefore, the magnitude of FAB can easily be calculated, which is equals to 500 Newton. Using the method of joint, you can see that we are able to calculate for forces acting on beam BC as well as beam AB. So as the calculated magnitude is positive, then the presumed direction of the forces is correct. Based on this force direction, beam BC would be in compressed state, while beam AB would be in tensile state. Okay, notice the direction of the forces. So basically, that is how you perform the computational analysis on a 2D structure by using the method of joints. Now, why don't you try this and find the unknown forces at joint A and joint C on your own? Okay, all the best. Until then, see you later, alligator.